In the vast silence of the cosmos, there exists a blue planet, traveling at a distance of almost 150 million kilometers from its star. It rotates at such a perfectly calibrated speed that one half doesn't have time to freeze solid, while the other doesn't incinerate. This world has a moon of ideal dimensions, causing gentle tides on its surface, an atmosphere with precisely 21% oxygen content, and a magnetic field that, like an invisible dome, deflects deadly solar radiation. Let's take a journey through the most astonishing coincidences in the universe. We'll delve into the forces that keep you anchored to the planet's surface. We'll explore the perfect confluence of circumstances that led to the emergence of your DNA and discover why you breathe the only known gas mixture in space capable of sustaining life. If you're ready to rethink everything you thought you knew about your place in the cosmos, prepare for a deep dive. Imagine yourself on Mercury's surface, where the ground temperature soars to nearly 430 degrees Celsius, hot enough to melt zinc in mere moments. Then, mentally transport yourself to Mars, where the thermometer plummets to a chilling minus 130 degrees, and your very breath would freeze into ice the moment it left your lungs. Between these two extremes, one fiery, the other icy, lies a planet perfectly positioned at an impeccable distance from its star. Not too hot, not too cold, just right for liquid water to exist on its surface. This narrow band around every star is what astronomers call the habitable zone, though it also has a more evocative name, the Goldilocks zone, named after the fairy tale character who found her porridge to be just right. And Earth, as it happens, resides precisely in this cosmic sweet spot, where the conditions for life to emerge are optimal. What makes this so incredible is the fact that a shift in Earth's orbit of just 5% closer to the Sun would cause our oceans to evaporate, while moving the same 5% further away would condemn them to eternal freezing, transforming the planet into an icy ball. We exist within a corridor of space whose width does not exceed 3% of the total diameter of our solar system. This can be compared to walking a tightrope stretched across the Grand Canyon. One wrong move in either direction, and a fall is inevitable. Yet Earth has maintained its balance on this cosmic tightrope for over 4 billion years, without making a single fatal error. When our solar system was first forming from a swirling cloud of gas and dust, the position of each planet was determined by a multitude of random factors. The nebula's rotational speed, the density of its individual regions, the gravitational influence of passing stars, and even the precise moment our sun ignited. All these variables had to align in a perfect combination for Earth to find itself within its narrow habitable zone. Our closest neighbor, Venus, missed by just 40 million kilometers, and this small deviation turned it into a hellish world with rains of sulfuric acid and atmospheric pressure capable of crushing a submarine. Mars missed by a comparable distance in the opposite direction and became an icy desert where liquid water hasn't appeared on the surface for billions of years. And yet, among countless possibilities, Earth settled into precisely the spot where complex chemistry could thrive, where water cycled, and where temperatures remained stable for the formation of the first living cells. Astronomers have calculated that the probability of such conditions arising by chance is so infinitesimally small that it would require a number with more zeros than atoms in the observable universe to write it down. This became the first great coincidence that made life possible. However, compared to what awaits us next, the ideal distance from a star is just the simplest part of this puzzle. In our night sky shines a satellite whose size and position are so impeccably chosen that it has determined the course of every day on Earth since its very inception. Our moon is located 384,000 kilometers away, precisely the distance needed for its visible disk to almost perfectly align with the sun's disk during solar eclipses. This unique cosmic alignment allows us to study the solar corona and has helped scientists understand how stars work. However, such celestial geometry is merely the beginning of the moon's contribution to the existence of life. Every 6 hours, one can observe the satellite's gravity pulling the oceans, moving them along the coast in a rhythm that has remained unbroken for 4 billion years. These tides don't just create picturesque beaches, they stir nutrients in the seawater, enriching it with chemical elements essential for sustaining life. Without this stirring, our seas would turn into stagnant pools, unsuitable for survival. The moon's gravitational pull also serves as a cosmic metronome that stabilizes Earth's rotational speed. Mars, for instance, has 2 tiny moons whose gravitational influence is barely noticeable, causing its axis of rotation to wobble wildly. Sometimes its poles end up pointed directly at the sun, causing temperature swings of hundreds of degrees, capable of wiping out any emerging life. But our large moon keeps our planet's tilt at an angle of 23.5 degrees, ensuring gentle seasonal changes, which has allowed life to spread across the entire planet. If the moon were to disappear, Earth would begin to tumble chaotically through space, like a broken spinning top. Scientists have calculated that for the creation of stable tides and the maintenance of its axis of rotation, a moon must have a very specific size relative to its planet. One that is too small, like Mars's, won't have the desired effect, while one that is too large would cause catastrophic consequences. If a moon were too massive, its tidal forces would rip apart the Earth's crust and evaporate the oceans. Our moon has the perfect ratio. Its size is exactly 1/4 the diameter of Earth, a proportion unique to the entire solar system. By comparison, Jupiter's moons are negligibly small next to their gas giant, and even Charon, Pluto's largest moon, achieves only half of that ratio relative to its planet. The incredible precision of our moon's size becomes even more astonishing when we recall the history of its formation. 4.5 billion years ago, the protoplanet Theia, comparable in size to Mars, collided with the young Earth at a perfect angle and an ideal speed. Too direct a hit would have led to the mutual destruction of both celestial bodies, whereas an overly glancing blow would have simply flung Theia back into space. Yet the collision occurred in just such a way that exactly the right amount of matter was ejected into orbit, which was needed to form a satellite of the correct size and at the proper distance. The likelihood of such an event is comparable to hitting a dart thrown from space precisely into the bullseye of a target on Earth. Therefore, tonight, when you gaze upon that familiar silvery disk, remember that you are witnessing a second great coincidence that made your very existence possible. Still further, in the depths of space, a far more formidable guardian watches over our world. In an orbit 2.5 times farther from the Sun than Earth's, revolves a giant capable of swallowing our planet like a marble dropped into a basketball. Jupiter's mass exceeds the combined mass of all other planets in the solar system put together. Thanks to its colossal mass, Jupiter possesses the most powerful gravitational field, which for billions of years has been working like a sort of cosmic vacuum cleaner. It attracts comets and asteroids that otherwise could have collided with Earth, causing catastrophic destruction. Astronomers regularly observe how this giant intercepts yet another wandering body from deep space. In 1994, scientists observed a unique event. Comet Shoemaker-Levy 9, having fragmented, crashed into Jupiter's atmosphere. The power of the explosions from these collisions surpassed the size of Earth itself, and the released energy was greater than that of all nuclear bombs detonated simultaneously. This comet was originally headed towards the inner solar system, and our world could very well have been its target, but Jupiter's gravity saved Earth from a civilization-ending impact. This protective function is constantly at work, though on a smaller scale. Jupiter deflects countless asteroids that would otherwise be heading towards our planet. But its influence isn't limited merely to intercepting space debris. Jupiter's powerful gravitational field helped shape the entire architecture of the solar system, stabilizing the orbits of the smaller planets and preventing their collisions. Computer modeling shows that without Jupiter's gravitational influence, Earth's orbit would eventually become unstable, and over millions of years, our planet would have fallen into the Sun. The gas giant sits at the perfect distance. It provides maximum protection without disrupting Earth's orbit. Move Jupiter closer to the Sun, and its gravity would hurl Earth into the cold expanse of space. Push it further away, and it would cease protecting us from the asteroid belt located between it and Mars. This belt contains millions of rocky chunks, some of which reach the size of mountains, and without Jupiter acting as a gravitational shepherd, they would scatter throughout the inner solar system, turning Earth into a prime target. Scientists have discovered that most star systems in our galaxy lack gas giants positioned like Jupiter. Instead, what they often find are hot Jupiters, massive worlds orbiting so close to their stars that they create gravitational chaos, dooming Earth-like planets to either fall into the star or be ejected into interstellar space. Our own Jupiter formed at an ideal distance and maintained its stable orbit for 4 billion years without migrating inwards toward the system's center, as is characteristic of most gas giants. This stability allowed life on Earth to evolve without the constant threat of collisions capable of causing mass extinctions. The timing of its formation also perfectly coincided with Earth's development, providing protection precisely at the moment when it was needed for the emergence of oceans and atmosphere. This cosmic protector is the third great coincidence in our unique solar system. But even with such a mighty guardian, Earth is continuously exposed to deadly cosmic radiation, capable of sterilizing all life in minutes. At a speed of over 1.5 million kilometers per hour, a stream of charged particles races towards our planet, so dangerous it could strip away our atmosphere and turn Earth into a lifeless rock, similar to Mars. If this solar wind were to reach the surface, it would destroy all life on the planet in mere moments. The only reason you can stand out in the open, unafraid of deadly radiation, is an invisible magnetic field. Our planet generates it on its own, and it deflects these particles back into space, working like a gigantic force field. Deep beneath the surface, at a depth of almost 2,500 kilometers, within Earth's liquid outer core, molten iron churns and moves, heated to temperatures exceeding that of the Sun's surface. The planet's rotation forces this molten metal to move along complex trajectories, which generates powerful electrical currents. These very currents create the magnetic field, which stretches into space for 60,000 kilometers. Our planet is enveloped by an invisible magnetic bubble known as the magnetosphere, which acts as a shield, deflecting streams of deadly particles from the Sun. When these particles interact with our magnetic field, polar auroras are born, magnificent tapestries of green and blue light in the polar skies. These captivating phenomena are essentially visible proof of how Earth's magnetic field successfully repels the onslaught of solar radiation. Once, Mars, like Earth, possessed its own magnetic field. However, due to its smaller size, its core cooled and solidified billions of years ago. Deprived of its liquid core, which generated electric currents, Mars lost its magnetic shield. As a result, the solar wind gradually stripped away most of the Martian atmosphere, leaving behind only thin and cold air that renders the planet uninhabitable. Venus also lacks a protective magnetic field, and despite having a dense atmosphere, its surface is bombarded by radiation lethal to any known life form. Only on Earth has a unique combination of planetary size, core composition, and rotational speed allowed for the sustained presence of a magnetic field over billions of years. The strength of this field is perfectly balanced for the existence of life. Were it too weak, solar radiation would have, over time, stripped away our atmosphere, as happened on Mars. If the field proved too powerful, it would trap so much solar energy that the upper layers of the atmosphere would overheat, literally scorching the planet's surface. Scientists have determined that the intensity of Earth's magnetic field has remained surprisingly constant throughout its history, varying by less than 20%. This stability persisted even during periods of magnetic pole reversals when the field temporarily weakened. It is this reliable protection that has ensured the continuous evolution of life over 4 billion years. Furthermore, the magnetic field safeguards the very fragile chemical basis of life itself. High-energy cosmic radiation is capable of destroying DNA and other complex molecules. Without our magnetic shield, the building blocks of life would decay faster than they could form, making the emergence of evolution impossible. This invisible shield is the fourth great coincidence making Earth habitable, but it protects us only from external threats. The air you are breathing right now is an even more finely tuned system. Take a deep breath and consider. You are inhaling a gas mixture so precisely balanced that changing any of its components by just a few % would render our planet uninhabitable. Our atmosphere consists of exactly 21% oxygen, 78% nitrogen, and trace amounts of argon, carbon dioxide, and other elements. This is a unique combination, the only one known in the universe capable of sustaining complex life. Imagine if oxygen levels were to rise to 25%. Then any spark would lead to colossal fires, capable of scorching entire continents. An excess of oxygen would make organic matter so highly flammable that lightning strikes would trigger global firestorms, hindering the formation of forests and grasslands. But if oxygen levels dropped to 16%, you simply wouldn't be able to get enough of it to fuel your brain and muscles. Even with normal breathing, you would slowly suffocate. Nitrogen, which makes up the bulk of our atmosphere, doesn't just act as a diluent, maintaining a safe concentration of oxygen. It creates the atmospheric pressure vital for water on Earth's surface to remain in a liquid state. Without enough nitrogen, water would simply evaporate into space. On the other hand, an excess of nitrogen would create such high pressure that water evaporation would become impossible, thus disrupting the cycle that distributes moisture across the entire planet. The minuscule amount of carbon dioxide in the air, currently about 400 parts per million, provides precisely the level of greenhouse effect that keeps Earth's average temperature above freezing. If we were to double this concentration, an uncontrolled greenhouse effect would transform our planet into a Venus-like world. And if we were to halve it, ice would cover Earth from pole to pole, reflecting so much sunlight that it would freeze solid forever. This unique atmospheric composition formed over billions of years through incredibly complex processes. Gradually, photosynthetic bacteria began releasing oxygen as a byproduct, slowly altering the air's composition over 2 billion years. This transition from an oxygen-free environment to one saturated with oxygen became one of the most dramatic chemical transformations in Earth's history. During what's known as the Great Oxygenation Event, oxygen levels surged so sharply that it led to the extinction of most organisms living at the time, but at the same time, it paved the way for the evolution of those who adapted to breathe oxygen. It's astonishing that the concentration of oxygen in our atmosphere has consistently remained at 21% for hundreds of millions of years now. This occurs despite constant geological and biological processes, which by all accounts should have altered this balance. Such stability suggests the existence of a global feedback system that automatically regulates the air's composition, maintaining conditions suitable for life. Furthermore, our atmosphere provides a perfect level of protection from destructive ultraviolet radiation while remaining transparent to visible light that reaches the surface. This so-called optical window not only makes photosynthesis possible, but also protects the DNA of living organisms from damage. As you breathe this perfect mixture of air, you are relying on the fifth great coincidence, without which life would be unthinkable. However, the most astonishing substance on our planet isn't air, but water, of which you are made. Every single drop of it violates the fundamental laws of chemistry in such a way that it allows life to exist. According to all chemical calculations, at Earth's temperatures, water should be a gas. When comparing its molecular mass and structure to similar compounds, such as hydrogen sulfide, all formulas indicate that water should boil at a temperature of -73 degrees Celsius and exist in the atmosphere exclusively as vapor. Against all odds, water remains liquid precisely within the temperature range essential for life to exist. This impossible behavior is explained by hydrogen bonds, weak electrical connections between water molecules that form and break billions of times per second. It is these bonds that endow water with unique properties, unparalleled anywhere else in our known universe. One such property is its expansion upon freezing, allowing ice to float rather than sink. If ice behaved like other solids and sank to the bottom, lakes and oceans would freeze from the bottom up. This would transform our planet into an icy sphere that would never thaw. Floating ice forms a heat-insulating layer, keeping the water beneath it in a liquid state and allowing life to survive even ice ages. Water also holds heat better than almost any other substance, making it an ideal thermoregulator for living organisms. Your body is composed of 60% water, and it is its heat capacity that maintains a stable internal temperature, even when environmental conditions change drastically. The oceans, meanwhile, accumulate a colossal amount of solar energy and slowly release it, moderating the planet's climate and preventing extreme temperature swings that are destructive to most forms of life. Water's chemical properties are no less astonishing. It dissolves more substances than any other liquid, which is why it's called the universal solvent. This ability allows water to carry nutrients, minerals, and metabolic waste within your body, as well as to transport chemical compounds across entire ecosystems. Blood, plant sap, and intracellular fluid, these are all aqueous solutions delivering essential substances wherever they are needed. Water molecules also form an ideal framework for complex biological molecules. DNA, proteins, and other key cellular components acquire their functional forms only through interaction with the water surrounding them. The water cycle in nature itself appears as if it were specifically designed to sustain life. This global mechanism evaporates water from the oceans, purifies it in the clouds, and delivers it to land in the form of fresh precipitation. A planetary-scale distillation system operates flawlessly for billions of years, constantly recycling and purifying the water that we all depend on. Water is the sixth great coincidence making your existence a reality. But even this wondrous material would be useless if Earth didn't rotate at a perfectly precise speed. Our planet completes one rotation in 24 hours, and this calibration is so precise that a deviation of just a few hours would render it uninhabitable. Imagine Earth rotating twice as fast, with a day lasting only 12 hours. This accelerated spin would create constant winds exceeding 480 kilometers per hour, which would tear down any buildings and rip trees from their roots. Life on land would be impossible in such a perpetual hurricane. Now imagine the opposite. Earth rotating twice as slowly, with the day lasting 48 hours. During the long daytime hours, the sun would scorch the surface to temperatures above 90 degrees Celsius, whereas the night side would freeze to minus 101 degrees. Such colossal temperature fluctuations would generate storms of such destructive power that even the most powerful hurricanes would seem like a gentle breeze in comparison. Our planet's current rotation speed, with its 24-hour daily cycle, creates a perfect thermal balance. It allows the sun to warm the Earth's surface without permitting overheating, and then gives the planet enough time to cool down, but not to freeze solid. This rhythm remains remarkably stable for billions of years. Although the Moon's gravitational pull gradually slows Earth's rotation by approximately 1 second every 50,000 years, this constant daily cycle has underpinned all aspects of life on the planet. Even the biochemical processes within your cells obey circadian rhythms tuned to the planet's 24-hour rotation. The Earth's rotational speed also gives rise to the Coriolis effect, which shapes weather systems and ocean currents responsible for distributing heat across the globe. Additionally, this rotation generates Earth's magnetic field by stirring molten iron in the planet's core. A slower rotation would weaken this magnetic shield, allowing destructive solar radiation to strip away the atmosphere. Mars rotates at nearly the same speed as Earth. Its day lasts 24 hours and 37 minutes. However, the red planet lacks a large moon to stabilize its rotation, which causes Mars's axis to undergo significant wobbles over millennia. This instability triggers extreme climate changes, preventing the formation of stable ecosystems. Venus, in contrast, rotates so slowly that its day lasts 243 Earth days, that is, longer than its year. Such a slow rotation allows the sun to heat one side of the planet for months, which creates hellish conditions on its surface with temperatures exceeding 480 degrees Celsius. Earth's rotation speed is the seventh great coincidence that made life possible. However, our planet's axis of rotation has a tilt, creating even more favorable conditions. Earth is tilted precisely by 23.5 degrees, which ensures a gentle change of seasons, allowing life to thrive across the entire planet for billions of years. Without this tilt, there would be no change of seasons on Earth. The equator would remain scorching hot year-round, and the poles would be eternally locked in ice, forming extreme climatic zones and confining life to a narrow band in the mid-latitudes. If the tilt increased to 45 degrees, the change of seasons would become so severe that it would sterilize much of the planet. While Mars's axial tilt is 25 degrees, very close to Earth's, it lacks a large moon to stabilize this position. As a result, over millennia, the Martian axis has fluctuated between 15 and 35 degrees, causing drastic climatic shifts. Earth's axial tilt of 23.5 degrees creates a perfect balance. Summer heat melts winter snow and ice, supplying plants and animals with fresh water, while winter frosts curb the spread of harmful bacteria and pests. Spring and autumn serve as transitional periods, allowing living organisms to gradually adapt to changing conditions. These seasonal rhythms underlie complex ecosystems, where different species depend on each other's seasonal behaviors. Ocean currents also depend on seasonal temperature changes, driven by Earth's tilt. Agricultural cycles, which enabled human civilization to emerge and flourish, are fundamentally based on these seasonal shifts. Without the predictable change of seasons, agriculture would be impossible. The Earth's ideal axial tilt is the eighth great coincidence that makes the existence of complex life possible. However, our planet's location in the galaxy offers an even grander level of protection. Earth orbits the Sun in the quiet suburbs of the Milky Way, precisely in the region where life can survive, avoiding cosmic threats that would sterilize planets near the galactic center. Our solar system is located 26,000 light-years from it, in a zone astronomers call the Galactic Habitable Zone. If we were located twice as close to the galactic core, lethal radiation from the supermassive black hole at its center would strip away Earth's atmosphere. And if we were twice as far away, our corner of space simply wouldn't have enough heavy elements such as carbon, oxygen, and iron, which are absolutely essential for the emergence of life. Near the galactic center, stars are so densely concentrated that their gravitational interactions would constantly disrupt planetary orbits. What's more, massive stars in the core burn out in just millions of years and then explode as supernovae, generating waves of radiation capable of destroying any nascent life. At the very heart of the galaxy lurks a black hole, whose mass is 4 million times that of the Sun. This monster periodically swallows nearby stars and gas clouds, erupting with bursts of X-ray and gamma radiation powerful enough to strip away the ozone layers of planets hundreds of light-years away. Earth's distance from this cosmic furnace safely protects us. Our solar system also travels through the galaxy at a perfectly calibrated speed, allowing it to avoid most dangers. We complete one orbit around the center of the Milky Way in 230 million years, moving fast enough to avoid the spiral arms, where most supernova explosions are concentrated. Even the size and type of our galaxy favor the existence of life. The Milky Way is massive enough to produce heavy elements, but not so large that its core becomes overly active and dangerous. Our safe location within the galaxy is the ninth great coincidence that has made life possible. However, it turns out that even the fundamental laws of physics themselves seem to be precisely tuned for our existence. The universe operates according to fundamental constants that are fine-tuned with incredible precision, as if someone set the cosmic dials to the perfect values necessary for the emergence of matter, energy, and life. For instance, gravity holds you to Earth with a force that allows stars and planets to form without simultaneously tearing atoms apart. If the force of gravity were increased by just 1 part in 10 to the 37th power, stars would burn out in millions, not billions, of years, leaving no time for life to evolve. Similarly, the strong nuclear force binds protons and neutrons within atomic nuclei with a strength that allows the entire periodic table of elements to exist. If this force were slightly weaker, atomic nuclei would disintegrate and only hydrogen would remain in the universe. Increase its power, and all the hydrogen in the universe would convert into heavier elements, leaving no fuel for stars, nor water for life to emerge. In turn, the electromagnetic force dictates how atoms combine into molecules. If its magnitude were off by merely 4%, carbon atoms would lose the ability to form complex molecular chains that underpin living organisms. Even the expansion rate of the universe itself seems perfectly fine-tuned. If it expanded too rapidly, matter would be distributed so sparsely that gravity wouldn't be able to coalesce it into galaxies and stars. If it expanded too slowly, the universe would collapse back into a singularity long before stars could even begin to form. Cosmologists have calculated that the fundamental constants of nature must fall within astonishingly narrow ranges of values for the universe to be able to support life. The probability of such conditions arising by chance is so vanishingly tiny that it would require more universes than there are atoms in the observable universe. And this perfect calibration is the 10th great coincidence that makes our very existence a reality. Some scientists hypothesize that our universe is just one of countless others in a giant multiverse, and we simply happen to be in that rare corner where the constants coincidentally aligned just right. Others suggest that these constants are a consequence of deeper physical laws, which inherently predetermine their values, permitting life to emerge. However, gravity itself deserves a separate, more detailed examination. The force of gravity shapes every single structure in the universe, and its magnitude is tuned so precisely that even the slightest deviation would make the existence of stars, planets, and life itself impossible. Imagine if gravity were 2 times more powerful. Stars would collapse under their own weight and burn through their nuclear fuel in millions of years instead of billions. Stronger gravity would also flatten any rocky planets into dense metallic spheres. Now, imagine the opposite scenario where gravity is 2 times weaker. In that case, clouds of cosmic gas would never compress with enough force to ignite nuclear fusion. The universe would remain a dark and cold place. In our universe, gravity is calibrated with such precision that it allows stars to burn stably for billions of years, supporting stable planetary orbits. This perfect balance provides the conditions for stellar nucleosynthesis, the process during which heavy elements are created in the cores of stars, such as carbon, oxygen, and iron. Gravity also sets the limit on the size of planets suitable for life. Too strong a gravitational pull creates such high atmospheric pressure that water cannot exist in liquid form. If gravity is too weak, the atmosphere escapes into space. The gravitational constant, it appears, is identical across the universe and has remained unchanged since the Big Bang. This universality allows the same physical processes that shaped Earth to operate throughout the cosmos. Moreover, gravity gives rise to tidal forces that have influenced Earth's evolution in countless ways. The Moon's gravitational pull creates oceanic tides, which may have formed the very bodies of water where ancient life first made the transition from water to land. These same forces are gradually slowing our planet's rotation. The ability of birds and insects to fly is directly linked to the precise strength of gravity. It is weak enough for lift to overcome it, but strong enough to create the air resistance necessary for controlled flight. This same fundamental force also operates on grand cosmic scales, holding together gigantic clusters of galaxies. The perfectly calibrated force of gravity is also a necessary condition for the formation of black holes in the final stage of massive stars' existence. These objects serve as a kind of cosmic recycling center, scattering heavy elements throughout the universe. Thus, gravity acts as the 11th great coincidence that makes our existence a reality. And it operates in perfect harmony with nuclear forces, the very ones that create the elements essential for life. Deep inside every star, these forces work with incredible precision, synthesizing the chemical elements from which your body is also built. Their magnitude is perfectly calibrated for the production of carbon, oxygen, and all other atoms, without which life would be unthinkable. It is the strong nuclear force that is responsible for holding protons and neutrons within atomic nuclei, counteracting the electromagnetic force that seeks to repel positively charged protons from one another. This cosmic balance of forces is so exquisitely fine-tuned that if the strong nuclear force differed by just 2%, the synthesis of carbon atoms would become impossible. Deep within massive stars, where temperatures reach 100 million degrees, hydrogen nuclei undergo fusion reactions, gradually forming heavier elements. Initially, hydrogen is transformed into helium. Next, helium nuclei merge, producing beryllium, an extremely unstable element which decays almost instantaneously unless in the briefest moment of its existence it manages to capture another helium nucleus. This is precisely how, through a process that astronomers initially considered practically impossible, carbon is born. The existence of a nuclear resonance, which makes the formation of carbon possible, was theoretically predicted by astronomer Fred Hoyle long before its experimental confirmation. Hoyle calculated that a very specific energy level within its nucleus was necessary for carbon synthesis. When experimental physicists began their search, they discovered this level in precise accordance with Hoyle's calculations. It was precisely thanks to this resonance that carbon became a sufficiently abundant element to form the basis of all known biological molecules. Nuclear interactions are also responsible for the synthesis of oxygen. If the strong nuclear interaction were just a little more intense, all carbon would transform into oxygen too quickly, leaving no building blocks for organic life. And if it were slightly weaker, oxygen couldn't form at all. The end product of thermonuclear reactions in stars is iron, because its nucleus possesses exceptional stability. Such a perfect balance allows stars to shine stably for billions of years. When a massive star exhausts its nuclear fuel, it collapses and explodes as a supernova, scattering all the heavy elements it synthesized throughout the cosmos. The power of these stellar cataclysms is so immense that it allows for the formation of elements heavier than iron. In turn, the weak nuclear force governs the processes of radioactive decay, which heat Earth's interior and sustain the movement of tectonic plates. Deprived of this internal heat source, our planet would turn into a block of ice. These perfectly calibrated interactions are precisely the 12th great coincidence that made our existence possible. However, among the vast diversity of elements, one holds a particularly special significance for life. Carbon atoms are endowed with the unique ability to form strong bonds, both with each other and with other elements. This capability allows them to create the most complex chemical compounds, which form the basis of all known biology, structures unparalleled in the universe. Carbon's uniqueness lies in the ability of each of its atoms to form 4 stable chemical bonds. This property allows it to bond with other carbon atoms, forming chains, rings, and 3-dimensional structures of virtually limitless complexity and scale. No other element possesses such versatility. Even silicon, carbon's closest chemical analog, is only capable of forming long chains under controlled laboratory conditions. Thanks to its bonding ability, carbon can create millions of diverse molecules using just a few types of atoms. By combining carbon with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, you can obtain DNA, proteins, fats, carbohydrates, and any other molecules that form the basis of life. Carbon chemistry functions excellently in an aqueous environment, forming stable yet sufficiently flexible bonds. Carbon lies at the heart of DNA, the molecule that stores the genetic information of all living organisms. The double helix structure of DNA is directly dependent on carbon atoms that form its sugar phosphate backbone. It is this framework that lends stability to the molecule and enables the reading and copying of the genetic code. Proteins, which are molecular machines performing most biological tasks, fold into intricate 3-dimensional shapes, determined by the sequence of their carbon-containing amino acids. The carbon cycle unites all life on Earth, facilitating the movement of its atoms between the atmosphere, oceans, and living organisms. Plants absorb carbon dioxide from the air and, through photosynthesis, create organic molecules from it. Animals, in turn, consume plants and return carbon to the atmosphere through respiration, sustaining this cycle for billions of years. The sheer abundance of carbon in the universe is the result of precise nuclear resonances that allow stars to synthesize it from helium. Without these finely tuned physical processes, carbon would be too rare to support the complex chemistry of life. The unique properties of carbon are the 13th great coincidence that makes complex life possible. However, its very emergence required an even more incredible sequence of events. 4 billion years ago, in the warm waters of early Earth, molecules began to do something that had never happened before in the universe. They learned to copy themselves. This transition from simple chemistry to self-replication represents one of the most astonishing events in history. Scientists have calculated that the probability of a self-replicating molecule arising purely by chance is less than 1 chance in 10 to the power of 40,000, whereas in the entire observable universe, there are only 10 to the power of 80 atoms. The first self-replicating molecule faced an almost insurmountable challenge. It needed to be complex enough to carry instructions for its own creation, yet simple enough to spontaneously assemble from the early Earth's chemical broth. The DNA molecule, storing genetic information in modern organisms, is too complex to have formed spontaneously. That's why scientists hypothesize that life began with RNA, a simpler relative of DNA, capable of both storing information and catalyzing reactions. According to the RNA world hypothesis, at the dawn of our planet's existence, the oceans were filled with countless ribonucleic acids. As a result of an incredibly improbable chain of random events, a single, unique RNA molecule emerged, capable of creating its own, albeit imperfect, copies. These copying inaccuracies, known as mutations, sometimes gave rise to new RNA molecules that proved more adapted for survival and self-replication. The process of molecular evolution required maintaining a very delicate balance. The mutation rate had to be perfectly balanced to allow for improvements, yet still preserve the stability of the genetic heritage. The transition from an RNA world to a DNA world became possible thanks to another series of incredible coincidences. The DNA molecule is far more stable than its predecessor, but lacks the ability to self-catalyze its own replication process. Life had to create protein enzymes to copy DNA, but the synthesis of these very proteins required RNA mechanisms. This classic chicken and egg dilemma implied the highest degree of coordination. The emergence of the genetic code adds yet another layer of astonishing coincidences. This code, which translates DNA nucleotide sequences into protein amino acid sequences, is virtually identical in all living organisms on Earth. The emergence of self-replicating life marked the 14th grand coincidence that ultimately led to your appearance. However, to survive, it had to endure global catastrophes that repeatedly brought all living things to the brink of complete extinction. Throughout Earth's history, massive extinctions rock the planet, acting with the precision of a cosmic sculptor. Indeed, each such catastrophe destroyed precisely those species that hindered the development of more complex life forms. The most well-known of these events occurred 66 million years ago, when an asteroid approximately 10 kilometers in diameter collided with Earth, releasing energy equivalent to 10 billion atomic bombs. This cataclysm brought an end to the age of dinosaurs, but at the same time, it freed up numerous ecological niches. This allowed small mammals to begin a rapid development, which ultimately led to the emergence of the full diversity of modern species, including humans. Had it not been for that catastrophe, which happened at an incredibly opportune moment, dinosaurs would most likely still be the dominant force in the planet's ecosystems. The asteroid's impact acted as a kind of reset button for the evolutionary clock, giving mammals a chance to grow in size and develop complex brains, which, in turn, laid the foundation for the emergence of human intelligence. The Great Dying, which occurred 250 million years ago, was even more massive. It resulted in the extinction of 96% of all marine species and 70% of terrestrial vertebrates. Nevertheless, it was this very catastrophe that paved the way for small reptiles to evolve into dinosaurs, which, in turn, set the stage for the future dominance of mammals. Each major extinction event eliminated dominant life forms that held back the development of other groups of organisms. The causes of these mass extinctions appear like a list of perfectly synchronized cosmic and planetary cataclysms. Gigantic volcanic eruptions, asteroid impacts, abrupt climate shifts. And yet, despite all this, life bounced back time and again after disasters, each time becoming even more complex and diverse. This cyclical process suggests that mass extinctions serve as a kind of reset button for evolution. Without such periodic upheavals, evolution might have reached a dead end. The species Homo sapiens emerged under the harsh conditions of the last ice age. This epoch was marked by a series of climatic cataclysms that compelled our ancestors to evolve, developing larger brains, refining their tools, and building complex social connections. And these timely disasters are considered the 15th great coincidence in the planet's history. However, one solitary evolutionary innovation fundamentally transformed the way life operates on Earth. 3 billion years ago, microscopic bacteria living in ancient oceans mastered a unique chemical process that transformed our planet from a lifeless rock into the vibrant biosphere we see today. These ancient cyanobacteria discovered a way to capture the energy of sunlight and use it to synthesize organic molecules from water and carbon dioxide. This process, known as photosynthesis, provided access to a new energy source that didn't rely on finite chemical compounds. Prior to its emergence, life subsisted on an extremely meager supply. Such an energy deficit kept life primitive and rare. Photosynthesis unlocked an energy resource that was 10,000 times larger than all that had been available to living organisms before it. Sunlight strikes the planet's surface with such colossal power that the energy Earth receives in just 1 hour would be enough to provide for all the needs of human civilization for an entire year. Cyanobacteria managed to tap into this inexhaustible reservoir, thereby laying the foundation for all subsequent complex life. At first glance, the formula for photosynthesis is deceptively simple. The combination of carbon dioxide, water, and sunlight yields sugar and oxygen. However, hidden behind this simplicity is one of the most sophisticated molecular mechanisms ever created by evolution. The photosynthetic apparatus comprises dozens of precisely arranged proteins and pigments whose coordinated work allows it to capture light energy and convert it into chemical energy. The most astonishing aspect of photosynthesis is its ability to split water molecules, one of the most stable chemical compounds in the universe. To split water requires a tremendous amount of energy. And yet, cyanobacteria learned to do this using only sunlight. It was this very reaction, releasing oxygen as a byproduct, that initiated a global transformation of Earth's atmosphere. For over 1 billion years, photosynthetic bacteria continuously enriched Earth's atmosphere with oxygen while simultaneously absorbing carbon dioxide. This event, known as the Great Oxygen Catastrophe, proved devastating for most life forms existing at the time. They had evolved in an oxygen-free environment, and for them, oxygen was toxic, much like cyanide. Thus, the rising concentration of oxygen triggered the planet's first ever global ecological collapse, obliterating entire ecosystems of ancient microorganisms. Nevertheless, It was precisely this atmospheric transformation that created the conditions for the emergence of complex life. Organisms that utilize oxygen for respiration are capable of extracting 20 times more energy from food than their anaerobic counterparts. This energy abundance allowed living creatures to grow larger, move faster, and develop complex structures such as brains, eyes, and intricate nervous systems. Furthermore, photosynthesis led to the formation of the ozone layer, which shields the planet's surface from deadly ultraviolet radiation. In the upper layers of the atmosphere, oxygen is transformed into ozone by the sun's radiation, creating a protective screen. It was this very shield that, over time, allowed life to leave the safe ocean depths and begin colonizing land. The emergence of photosynthesis required an entire chain of highly improbable molecular innovations. Light-harvesting complexes needed to learn how to capture photons and transfer their energy without dissipating it as heat. Reaction centers had to master using light energy to initiate chemical processes that, under normal conditions, require very high temperatures. Finally, a mechanism had to emerge capable of breaking bonds in one of the most stable molecules in nature: the water molecule. Modern photosynthesis boasts nearly 100% efficiency, converting almost every absorbed photon into useful chemical energy. Such a degree of optimization speaks volumes about billions of years of evolutionary refinement. It's astonishing, however, that the fundamental mechanism of photosynthesis seems to have emerged very early in Earth's history and has remained virtually unchanged ever since. The photosynthetic revolution stands as the 16th grand coincidence that paved the way for complex life to evolve. Yet, this biological innovation could only realize its full potential because Earth's geology had prepared the perfect conditions for it. Right beneath your feet, gigantic blocks of rock, known as tectonic plates, are constantly shifting across the planet's surface at the same rate your fingernails grow, continuously renewing the Earth's crust and sustaining conditions favorable for life. Plate tectonics is a planetary conveyor belt that has been operating non-stop for over 3 billion years. In the zones of underwater volcanic ridges, where molten rock rises from the mantle, new ocean floor is formed. This new crust spreads apart, carrying the continents along like passengers on a giant, slow-moving raft. In places where oceanic plates meet continental ones, the denser oceanic crust subducts back into the planet's interior, completing the recycling cycle. This global geological system plays a crucial role in regulating Earth's climate by controlling the concentration of carbon dioxide in the atmosphere. When carbon dioxide levels rise, it dissolves in rainwater, forming a weak carbonic acid, which intensifies the weathering of rocks. During this weathering, carbon dioxide is removed from the atmosphere and stored as limestone and other sedimentary formations. When carbon dioxide levels drop, the weakening of weathering processes allows volcanic emissions to gradually restore its level in the atmosphere. Without plate tectonics, our planet would have become uninhabitable billions of years ago. Carbon dioxide could have either accumulated in the atmosphere to such an extent that an uncontrolled greenhouse effect would have turned Earth into something resembling Venus, where surface temperatures are capable of melting lead. Or it would have become permanently locked away in rocks, dooming the planet to eternal glaciation, where the greenhouse effect wouldn't have been able to keep water in a liquid state. Both Venus and Mars lack active plate tectonics, and both planets became uninhabitable, though for entirely opposite reasons. Venus's atmosphere contains an excessive amount of carbon dioxide, which creates surface temperatures exceeding 480 degrees Celsius. Mars, on the other hand, lost most of its carbon dioxide, which escaped into space because the planet lacked a geological recycling system capable of replenishing atmospheric gases. Plate tectonics also helps concentrate vital nutrients and minerals in locations accessible to living organisms. As tectonic plates collide, mountain ranges are formed, bringing fresh rocks to the surface. These rocks, as they undergo weathering, release phosphorus, nitrogen, and other elements vital for life. Furthermore, volcanic activity at plate boundaries carries materials from Earth's depths, forming fertile soils and deposits of valuable minerals. The movement of continents guided the evolution of life by creating and destroying land bridges between different regions. When continents drifted apart, populations of organisms became isolated and evolved along distinct paths. When continents collided, however, previously separated species entered into competition and interbred, greatly accelerating the pace of evolutionary change. Furthermore, plate tectonics generates Earth's magnetic field, driving the molten iron in our planet's outer core. This magnetic shield deflects deadly solar radiation and protects the atmosphere from being stripped away by solar winds. Mars, devoid of active plate tectonics, has, over billions of years, lost a significant portion of its atmosphere, swept away into space. The recycling of oceanic crust also plays a crucial role in maintaining the chemical balance of seawater. As oceanic plates subduct into the mantle, they carry with them salt and other dissolved substances. In turn, submarine volcanic activity returns these elements to the oceans, but in different proportions, preventing excessive salinity or chemical imbalance that would render the water uninhabitable. Over geological timescales, plate tectonics even influences climatic conditions by altering the arrangement of continents and oceans. The current configuration of continents ensures the global circulation of ocean currents, which distribute heat from the equator to the poles and thereby moderate our planet's climate. The speed of plate movement, apparently, is perfectly calibrated for sustaining life. Too rapid movement would lead to constant geological cataclysms, hindering the development of stable ecosystems. Too slow, and the geological recycling system would be unable to maintain the chemical composition of the atmosphere and oceans within habitable limits. This planetary system is the 17th great coincidence that makes life possible, working in perfect harmony with atmospheric processes. For 4.5 billion years, Earth's atmosphere has maintained precisely the ratio of greenhouse gases that was necessary to keep the planet warm enough for liquid water to exist, but not overheat to the point of a runaway greenhouse effect. The concentration of carbon dioxide, a key greenhouse gas, has varied significantly throughout history. Yet our planet somehow avoided both the catastrophic overheating that turned Venus into a scorching furnace and the global glaciation that could have perpetually encased it in ice. In the early days of the solar system, our sun was 25% dimmer than it is today. Such weak solar radiation should have led to the freezing of the oceans and the formation of a global ice sheet that would reflect so much light that Earth could never have warmed up again. However, the early atmosphere of our planet contained much more carbon dioxide, which created a powerful greenhouse effect that compensated for the lack of solar heat. As the sun gradually brightened over billions of years, the level of carbon dioxide in the atmosphere decreased with almost perfect precision, needed to maintain a stable temperature. This impeccable balance required incredibly precise timing. If carbon dioxide levels dropped too rapidly, the Earth would freeze over. If they dropped too slowly, our planet would overheat, repeating Venus's fate. The mechanism ensuring this delicate regulation is linked to rock weathering, which accelerates as temperatures rise and slows down as they fall. Higher temperatures enhance evaporation and rainfall and speed up chemical reactions, in which carbon dioxide dissolves into rainwater. This carbonic acid-rich water reacts with rocks, removing carbon dioxide from the atmosphere and sequestering it in limestone and other minerals. Thus, when temperatures on Earth rise, enhanced weathering extracts more carbon dioxide from the atmosphere, leading to the planet's cooling. When temperatures drop, the weathering process slows down, allowing volcanic emissions to gradually accumulate carbon dioxide and re-warm the planet. This natural thermostat has functioned flawlessly for billions of years, and the ice ages of the past 2 million years serve as a clear demonstration of its operation. During glacial epochs, vast quantities of water accumulated in continental glaciers, causing global sea levels to drop by more than 120 meters and exposing extensive areas of the continental shelf. This led to intensified rock weathering, which extracted excess carbon dioxide from the atmosphere and contributed to maintaining cold climatic conditions. Conversely, during interglacial periods, rising sea levels submerged the shelves, reducing the area available for weathering. This allowed carbon dioxide concentrations to gradually increase, which eventually led to warming and the end of another ice age. What's more, this entire cycle was governed with astonishing precision by subtle fluctuations in Earth's orbit around the Sun. Other greenhouse gases were also maintained within narrow limits, ensuring the planet's habitability. Water vapor, which is the most abundant greenhouse gas, increases its concentration as temperatures rise and decreases it as they fall, forming a feedback loop that amplifies minor temperature fluctuations but prevents them from reaching extreme values. Methane, whose ability to trap heat is 25 times greater than that of carbon dioxide, is produced by biological activity and broken down by chemical reactions in the atmosphere. The balance between its production and breakdown remained stable enough to prevent both a runaway greenhouse effect and the complete loss of this vital planet-warming gas. Even the timeline of key atmospheric changes appears perfectly aligned with the course of evolution. The so-called oxygen catastrophe, or the Great Oxidation Event, occurred after oxygen-producing cyanobacteria emerged, but before the rise of complex organisms, for which oxygen was vitally important. This gave the planet time to adapt to the new atmospheric chemistry without triggering a mass extinction of oxygen-dependent life forms, which simply didn't exist at that time. This delicate balance of greenhouse gases can be considered the 18th of the great coincidences that have kept Earth habitable. However, it's precisely the time frame for the emergence of complex life that points to an even more astonishing aspect of our planet's design. The development of complex organisms on Earth occurred within a narrow temporal window, one that is rapidly shrinking because our sun grows hotter and brighter with each passing million years. Stars, like our sun, undergo a predictable life cycle during which their luminosity gradually increases over billions of years. Today, the sun emits 10% more energy than it did when life first emerged on Earth, and its brightness will continue to grow until, in approximately 5 billion years, it transforms into a red giant, a change that will cause our planet's oceans and atmosphere to evaporate. However, complex life won't have 5 billion years to evolve. The sun's steady increase in brightness means that Earth will become uninhabitable much sooner. In just about 1 billion years, intensified solar heating will trigger an irreversible greenhouse effect that will evaporate the oceans and strip away the atmosphere into space, turning Earth into a Venus-like world. This circumstance establishes a kind of cosmic deadline for the evolutionary process. Since its inception, life had about 3.5 billion years to develop intelligence and technology before the planet becomes uninhabitable. Astonishingly, complex life emerged and gave rise to intelligence almost at the last possible moment to fit within the allotted time. For the first 2 billion years of Earth's history, life remained simple and microscopic. Bacteria and algae dominated the planet. More complex cells with nuclei appeared only about 2 billion years ago, and multicellular organisms with specialized tissues and organs formed no earlier than 600 million years ago, utilizing nearly all the time resources available for complex evolution. The animal kingdom experienced an explosion of diversity during the Cambrian period 540 million years ago, when almost all major body plans existing even today were established. This evolutionary leap occurred precisely when conditions on Earth became stable enough to sustain complex ecosystems. Intelligence, however, emerged even later. It arose in human ancestors only a few million years ago, not long before solar radiation would make the planet too hot for life. Modern humans developed agriculture and created technology only in the last 10,000 years, a minuscule period of time against the backdrop of billions of years of life's existence. The emergence of intelligence appears to be a rare and difficult to achieve evolutionary outcome. Despite billions of years of evolution and countless species, only one branch of living beings on Earth developed intelligence capable of comprehending the universe and creating technology for space exploration. This suggests that intelligence might be an extremely improbable outcome of evolution, requiring very specific conditions for its development. Which means most planets may never give rise to intelligent life, even with billions of years to spare. The timing of these events becomes even more remarkable when we consider that human intelligence developed during the Ice Age, an era of climatic instability that created evolutionary pressure, fostering brain enlargement and the refinement of tools. These same climatic challenges that spurred human evolution are linked to long-term changes in Earth's orbit and atmosphere, which will ultimately render it uninhabitable. Modern humanity developed space technologies just as our planet entered the final 1 billion years of its habitable period. This timing gives our species the potential opportunity to leave Earth and resettle in other worlds before it becomes too hot, but only if we continue our technological development at the current pace. This narrow window for complex evolution stands as the 19th great coincidence in Earth's history. The exceptional nature of intelligence prompts deep reflection on how often life in the universe attains the level of consciousness. Over 4 billion years of evolution on Earth, intelligence capable of comprehending the universe's workings emerged only once. This fact allows us to hypothesize that consciousness might just be the rarest phenomenon in the cosmos. After all, life itself appeared on our planet almost instantaneously by geological standards, approximately 3.5 billion years ago, giving rise to millions of species with countless adaptations since then. And yet, only one species managed to develop the cognitive abilities to build telescopes, decipher DNA, and ponder its own place in the universe. This suggests that while life may be widespread in the cosmos, intelligence is likely an incredible rarity. Many evolutionary paths lead to successful survival, requiring neither a large brain nor complex thought processes. Bacteria have flourished for billions of years without possessing intellect, and insects dominate terrestrial ecosystems by relying on instinct rather than conscious thought. Even among animals possessing a nervous system, high intelligence remains the preserve of only a few evolutionary branches. Dolphins, elephants, and some primates demonstrate signs of self-awareness and the ability to solve problems. Yet none has created a language complex enough to accumulate knowledge across generations, or technologies capable of fundamentally altering their environment. The evolution of human intelligence was made possible by an incredibly specific sequence of ecological factors and genetic changes. Our ancestors inhabited African forests, which over time gave way to savannas, compelling them to adapt to life in open spaces. This transition spurred the development of upright walking, tool use, and social cooperation. All of this served as a catalyst for increased brain volume. Climatic instability during the Ice Ages created additional evolutionary pressure, fostering cognitive progress, as a rapidly changing environment rewarded flexibility, planning, and cultural learning rather than rigidly fixed instincts. The emergence of language was yet another unlikely breakthrough, definitively separating humans from other intelligent species. Language allows for the accumulation of knowledge across generations, triggering a mechanism of cultural evolution which operates far more quickly than biological evolution. This cultural acceleration gave humanity the opportunity to develop agriculture, writing, and subsequently science and technology. Yet, even after its emergence, the survival of intelligence was not guaranteed. Ancient human populations found themselves on the brink of extinction on multiple occasions. Genetic analysis reveals that all modern humans are descendants of a population which about 70,000 years ago might have numbered fewer than 10,000 individuals. The rarity of intelligence on Earth has profound implications for the search for extraterrestrial life. While simple life might exist on numerous worlds across the galaxy, civilizations capable of interstellar communication could be separated by colossal distances and vast spans of time. Just consider this. Human civilization has existed for only about 10,000 years against the backdrop of 4.5 billion years of Earth's history. If intelligence on other worlds arises just as infrequently, then the probability of two civilizations coexisting simultaneously, close enough for contact, becomes vanishingly small. What's more, the development of intelligence seemingly requires very specific planetary conditions, which might be rare in the universe. Earth's stable climate, the presence of a large moon, a protective magnetic field, and its location within the galaxy's habitable zone. All of this contributed to creating an environment where intelligence could evolve and survive. The uniqueness of human intelligence on Earth represents just one of the grand coincidences in a series of events that led to the emergence of consciousness. To estimate how often something like this might occur in other parts of the universe, in 1961, astronomer Frank Drake developed an equation. It attempts to calculate how many civilizations capable of communication exist in our galaxy, and vividly illustrates how many improbable factors must align for intelligence to arise. Drake's equation multiplies 7 different variables: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction of those planets where life emerges, the fraction of those where intelligence develops, the percentage of civilizations that create technology, and the average lifespan of such civilizations. When Drake first proposed his equation, astronomers knew practically nothing about planets orbiting other stars. Today, however, space telescopes have discovered over 5,000 exoplanets, proving that planetary systems are widespread throughout the galaxy. According to the latest data, almost every star hosts at least one planet, and many stars are surrounded by entire systems of worlds. However, the search for potentially habitable planets has proven to be a much more challenging task. Most of the exoplanets discovered are either gas giants, similar to Jupiter, or rocky worlds that orbit too close to their stars for liquid water to exist on their surfaces. The few Earth-like planets found in habitable zones often orbit red dwarfs, which bombard them with deadly radiation or hold them in tidal lock, dooming one side to eternal day and the other to perpetual night. For a planet to be considered habitable, it must meet a whole host of criteria beyond just suitable temperature and atmospheric composition. Key factors include plate tectonics, the presence of a large moon to stabilize its axis, a protective magnetic field, as well as a gas giant present to shield it from asteroids and its location in a quiet region of the galaxy. When astronomers apply this entire complex of conditions, the number of truly Earth-like planets rapidly diminishes. And some calculations show that worlds with all the prerequisites for complex life could be separated by hundreds or even thousands of light years. The spontaneous emergence of life still remains one of the greatest scientific mysteries. Despite decades of intensive research, scientists have been unable to create self-replicating molecules from inorganic chemical compounds in laboratory conditions. This fact suggests that the emergence of life may be an extremely rare phenomenon, occurring on only a vanishingly small percentage of formerly suitable planets. The evolution of intelligence, judging by the history of our planet, appears to be an even more improbable process. It took more than 2 billion years for complex cells with a nucleus to evolve from simple bacteria. Another 1 billion years passed before multicellular organisms appeared. Intelligence itself emerged only in the very last instant of Earth's biological history, appearing in just one species out of the millions that have ever inhabited the planet. The emergence of technological civilization adds yet another level of improbability. Humanity mastered agriculture only 10,000 years ago, and industrial technologies have emerged only within the last few centuries. A multitude of factors, from climate catastrophes and asteroid impacts to social collapse, could easily have interrupted this fragile technological development at any of its stages. The final parameter in the famous Drake equation asks about the lifespan of technological civilizations before they self-destruct or are wiped from the face of the planet by natural cataclysms. The history of human civilization is less than 1/100,000th of Earth's entire history. Yet in this brief period, we have already created weapons capable of destroying our species and technologies that provoke irreversible climatic changes. Modern calculations using updated data for the Drake equation lead to a pessimistic conclusion. Earth may turn out to be the only planet in our galaxy where intelligent life currently exists. Even if life itself is widespread throughout the universe, the unique sequence of events that led to the emergence of a technological civilization might be so rare that it occurs in any given galaxy less than once every 1 billion years. This sense of cosmic solitude may well explain why our decades-long search for extraterrestrial intelligence has so far yielded no results. Perhaps we are alone, not because life on other worlds is impossible, but because the path from the simplest organisms to a technological society is immeasurably more complex than we once imagined. The search for cosmic neighbors is, in essence, humanity's attempt to unravel that very grand coincidence that made our own emergence possible. However, some scientists propose an even more radical hypothesis to explain our apparent uniqueness: the multiverse theory. This concept posits that our world is just one of a countless multitude of others, each possessing its own physical laws and constants. In such a model, our perfectly life-sustaining cosmos ceases to be an incredible coincidence and becomes a statistically inevitable outcome. Imagine an infinite number of universes emerging one after another, where in each, the values of fundamental forces, such as gravity, electromagnetism, and nuclear interactions, are randomly set. In the vast majority of these worlds, the physical constants would be incompatible with the formation of matter, stable atoms, the burning of stars, or the creation of complex molecules, rendering them utterly lifeless. In some universes, gravity might be so powerful that stars would collapse into black holes immediately after their birth, without having the chance to synthesize heavy elements. In still others, conversely, gravity would be so weak that gas clouds could never condense into stars, leaving behind only dark and empty spaces, devoid of light and energy. In universes with different electromagnetic force parameters, atoms might not be able to hold together, or electrons wouldn't form stable bonds with nuclei, which would render any chemistry impossible. Our familiar periodic table of elements simply wouldn't exist. Its place would be taken by entirely different atomic interactions, incapable of supporting complex structures. If nuclear forces had different values, this would prevent the formation of carbon, oxygen, and other elements fundamental to life. Stars might burn too quickly and brightly to provide a stable energy source, or nuclear fusion might not ignite at all within their cores, dooming potential planets to eternal cold and darkness. And yet, assuming the existence of an infinite number of universes with random physical constants, it is statistically inevitable that some would emerge where all values turned out to be suitable for the formation of matter, stars, planets, and ultimately, life. We find ourselves in one of these rare, hospitable universes not because it was specially created for us, but because in any other, we simply could not have arisen. This so-called anthropic reasoning explains our cosmic good fortune without resorting to the idea of a higher design or incredible luck. The concept of the multiverse finds its confirmation in several areas of modern physics. For example, the theory of cosmic inflation suggests that our observable universe is merely one of many bubbles that formed in boundless space after the Big Bang. And each such bubble can possess unique physical laws. In turn, string theory, which aims to unify all the forces of nature, predicts a vast number of possible universes with varying configurations of extra dimensions and fundamental particles. The mathematical framework of string theory suggests the existence of a landscape comprising approximately 10 to the 500th power of probable universes. This number is so vast that the emergence of worlds where life is possible becomes highly probable. The concept of multiple worlds also finds support in quantum mechanics through its many worlds interpretation, according to which each measurement gives rise to parallel realities, realizing all possible outcomes, thereby creating an infinite tree of universes with every conceivable history and future possibility. Nevertheless, the multiverse theory faces fundamental challenges. By its very definition, other universes lie beyond our observation and direct verification, which places this hypothesis outside the realm of the scientific method. Critics note that an explanation based on an infinite number of unobservable worlds is no more satisfying than the idea of some cosmic creator. What's more, the theory doesn't explain why our universe is tuned not merely for life in general, but for that specific, complex, and long-lasting form of it that managed to evolve on Earth. Even if we concede the existence of many life-sustaining worlds, most of them would likely only support the simplest forms of existence, rather than the strikingly rich biosphere we see around us. Some scientists believe that the apparent fine-tuning might have a simpler explanation, one that doesn't require invoking a multiverse. Perhaps fundamental constants are interconnected by deeper physical laws, which then dictate values favorable for the emergence of life. Thus, the multiverse is merely one of the solutions to the mystery of the great coincidence that made our existence possible. The anthropic principle offers another approach to this problem. Its core idea is that the universe appears perfectly suited for life to us simply because only in such a universe could conscious observers capable of studying it have emerged. This line of reasoning forms an elegant logical loop, We find ourselves in a world perfectly suited for us because in any other world, we simply wouldn't exist to make such observations. Perhaps the very question about the reasons for such cosmic fine-tuning is devoid of meaning, much like asking why water is wet or why a triangle has 3 sides. The weak anthropic principle states that we perceive the universe as life-friendly solely because our own existence as observers demands it. This formulation explains our cosmic good fortune without resorting to the idea of a higher design or the multiverse hypothesis. We are here, and notice this fine-tuning precisely because it was a necessary condition for our existence. However, this line of reasoning leads to intriguing conclusions about the nature of reality and observation itself. If conscious observers play a pivotal role in determining the specific universe we perceive, then consciousness itself might not just be a byproduct of complex matter, but a fundamental property of reality. The strong anthropic principle takes this idea even further, suggesting that the universe must possess properties that allow for the development of life, because the existence of observers is somehow necessary for reality's very being. This idea is intimately intertwined with quantum mechanics, where the act of observation plays a crucial role in determining physical outcomes. According to some interpretations of quantum mechanics, the universe remains in a superposition of all possible states until conscious observation collapses this superposition into one single observable reality. From this perspective, observers don't merely passively contemplate the world, but actively participate in creating the reality they perceive. It is this observer dependence that could explain why the universe appears designed for consciousness. Perhaps worlds without observers never truly come into being, remaining merely unrealized possibilities within an infinite quantum superposition. The anthropic principle also makes us ponder the future of consciousness in the universe. If observers are necessary for the existence of reality, then the ultimate heat death of our world and the disappearance of all conscious life would mean not merely the end of awareness, but the end of reality itself as such. Some cosmologists hypothesize that highly advanced civilizations could survive the heat death of the universe by finding ways to preserve consciousness even after the stars fade away. These eternal observers would sustain the existence of reality simply by virtue of their presence and awareness. This principle becomes even more intriguing when applied to the evolution of human intelligence. It's possible that the rapid emergence of consciousness on Earth was not an accident, but a necessary consequence in any universe capable of supporting observers. In that case, intelligence might not be an improbable evolutionary quirk, but an inevitable outcome of physical laws. Nevertheless, the anthropic principle struggles to explain why our world is optimized not for just any form of consciousness, but for the complex, scientifically oriented intelligence characteristic of humans. Many simpler forms of consciousness could satisfy the observer requirement without needing the complex cognitive abilities that allow us to study cosmology. The principle also fails to provide an answer to the question of the apparent fine-tuning of myriad physical constants, which seem superfluous for sustaining even basic consciousness. It remains a mystery why the universe is calibrated in such a way as to engender not merely consciousness, but all the rich diversity of chemistry, biology, and physics that we observe. Skeptics consider the anthropic principle a form of tautological, unscientific reasoning, explaining the observed order of the universe by the simple fact that this order is a prerequisite for the explanation itself. In their view, the scientific method should focus on seeking causal mechanisms rather than on logical deductions based on our own status as observers. The anthropic principle is just one way to make sense of the 23rd great coincidence, the emergence of consciousness in living beings. However, within the scientific community, even bolder hypotheses have been put forth regarding the fundamental nature of our reality. These theories suggest that life could exist in forms drastically different from those we currently know. Even though Earth's biology is entirely based on carbon chemistry, scientists have theoretically posited the existence of alternative biochemical systems. Such systems could potentially support life in environments utterly lethal to everything we understand as living. For instance, silicon, which is carbon's closest chemical analog, is capable of forming long molecular chains structurally similar to biological polymers. Silicon-based life could successfully thrive in extremely high-temperature environments where carbon molecules break down, for instance, on the molten surfaces of planets orbiting close to their stars or deep within the atmospheres of gas giants. However, silicon chemistry has significant limitations, which make it less flexible compared to carbon chemistry. Silicon bonds are weaker and lose stability in the presence of water, which narrows the habitat for such life to arid worlds or requires the presence of liquid solvents other than water. In very low temperature conditions, where water turns into ice, ammonia could take on its role as a universal solvent. This substance remains liquid at temperatures down to -78 degrees Celsius, theoretically allowing biochemical processes to occur on icy planets far from their suns. For instance, on Titan, Saturn's largest moon, there are entire lakes of liquid methane and ethane, which could potentially serve as a cradle for exotic organisms. Some researchers also entertain the possibility of plasma-based life forms, which could inhabit the scorching atmospheres of stars or the magnetic fields of gas giants. These beings would not be composed of the familiar matter we know, but rather of organized structures of charged particles, their complexity driven not by chemical bonds, but by electromagnetic interactions. Another hypothetical possibility is crystalline life, capable of storing and processing information within the atomic lattice of minerals, rather than in organic molecules. Quantum life, theoretically, could exist as stable structures based on quantum entanglement. Such organisms would store and process information using quantum mechanical effects, not chemical reactions, and would live directly in a vacuum, remaining invisible to systems based on ordinary matter. Another alternative is presented by machine life, where artificial intelligence is able to evolve and reproduce without any connection to its biological origin. Even staying within the bounds of carbon chemistry, alternative biochemical scenarios are possible using different genetic codes. The existence of proteins with a non-standard set of amino acids, or fundamentally different mechanisms of metabolism and reproduction, proves that Earth's biology is merely one of many solutions to the challenge of organizing matter into self-replicating and evolving systems. The study of extreme conditions on our planet, where life has been discovered in environments once thought to be completely barren, stimulates the search for alternative biochemical pathways. Organisms thrive in boiling water, in metal-dissolving acid, in saline solutions of lethal concentration, and deep underground, in rocks where sunlight never penetrates. These extremophiles serve as proof that life is far more adaptable than we once believed, and they suggest that it could exist even in completely alien conditions. The discovery of life in Earth's most inhospitable corners significantly expanded our understanding of habitable zones around other stars by including previously dismissed possibilities. However, any alternative biochemistry must solve the same fundamental problems as carbon-based life: how to store information, how to acquire energy from its surroundings, and how to reproduce with sufficient accuracy to preserve the species, yet with enough variability for evolution. The study of alternative life forms is, at its core, humanity's attempt to discover whether the 24th grand coincidence, carbon-based biochemistry, is truly the only possible path to complex life, or if other solutions are widespread throughout the universe. Meanwhile, some scientists hypothesize that our entire reality, with all conceivable forms of life, might be part of an even more astonishing structure than we can possibly imagine. The simulation hypothesis posits that our universe, including planet Earth, all living things upon it, and human consciousness itself, is nothing more than a computer program. This program, according to the theory, is running on a technological platform created by a super-advanced civilization. The philosopher Nick Bostrom expanded on this idea, arguing that if any civilization reaches a level enabling the creation of detailed simulations of conscious beings, it would, most likely, run many such simulations for research, entertainment, or other purposes. This means that the number of simulated conscious beings will eventually significantly outnumber those who originated through natural evolution. This scenario makes it statistically probable that any conscious observer, including yourself, actually exists within a computer simulation. The rapid advancement in computer technology clearly demonstrates how such simulations could become a reality. Modern video games are already capable of creating strikingly realistic virtual worlds populated by characters with artificial intelligence, and virtual reality systems can deceive human senses, immersing a person into a completely fictitious environment. If computational power continues to grow exponentially, future civilizations could create computers capable of simulating entire universes with detail down to the quantum level. Such simulated worlds could host billions of simulated planets with life forms, whose consciousness would be indistinguishable from that of naturally evolved beings. The inhabitants of such a simulation would have no way of knowing their reality was artificial, unless their creators themselves chose to reveal that information. Moreover, the laws of physics, chemistry, and biology within the simulated world would be entirely consistent, as they would be programmed to follow specific rules, thereby creating the complete illusion of a naturally occurring universe. This concept also explains the so-called fine-tuning of physical constants necessary for the existence of life. If our universe is a simulation, then its parameters would have been deliberately designed by programmers who wanted to create interesting phenomena like stars, planets, and living organisms. In that case, this fine-tuning wouldn't be a surprising coincidence, but a conscious design choice by our creators. Moreover, the simulation hypothesis offers an interpretation for the puzzling aspects of quantum mechanics, where particles seemingly exist in multiple states simultaneously until they are observed. This behavior mirrors how computer programs conserve computational resources by precisely calculating the state of objects only at the moment they are measured. Some scientists have even proposed experiments to test this hypothesis, the goal of which is to search for a kind of pixelation or computational approximations at the smallest scales of spacetime. Much like a digital image pixelates when magnified greatly. However, any test of this theory runs into fundamental limitations, for sufficiently advanced creators would likely have designed their virtual universe to be indistinguishable from reality, anticipating any tests its inhabitants might devise. This hypothesis also raises profound questions about the nature of consciousness and self-identity. If your thoughts, memories, and experiences are merely informational structures within a computer program, does that make you any less real than a person who arose through evolution? Is a simulated consciousness identical to a biological one, or is it simply a very convincing imitation? Even if we do exist within a simulation, that doesn't make our reality any less meaningful to us as conscious beings. Love, suffering, discovery, and creativity will remain authentic experiences, regardless of where they occur, in a biological brain or in lines of code. The likelihood that we are simulated beings, created by incredibly advanced programmers, represents the ultimate expression of the intelligent design hypothesis. It posits that not only life, but all of reality could be the product of a deliberate creation by an intelligence that lies far beyond our comprehension. And even if that were the case, our existence within a program would still be a remarkable achievement. The creation of conscious, curious beings capable of reflecting on their own existence and striving to comprehend the nature of reality. But regardless of whether our reality is natural or artificial, our presence in the universe imposes obligations upon us that extend far beyond Earth. It matters not what brought us into being, a cosmic accident, divine design, or the work of brilliant programmers. Humanity now faces a fundamental responsibility to preserve consciousness and life beyond our home planet before it becomes uninhabitable. The ideal conditions that allowed life to emerge and flourish on Earth will not last forever. Approximately 1 billion years from now, the sun's intensifying radiation will trigger an uncontrollable greenhouse effect that will evaporate our oceans and destroy our atmosphere. But long before then, climate change, asteroid impacts, or other catastrophes could put an end to our civilization and all life. This cosmic time limit transforms space exploration from an interesting possibility into a vital necessity for survival. Humanity must develop the technologies to create self-sufficient colonies on other worlds within the relatively short time frame we have left before Earth becomes uninhabitable. The search for habitable exoplanets reveals that worlds like ours are exceedingly rare in the galaxy. Most planets are gas giants, frozen blocks of ice, or scorching hot rocks orbiting too close to their stars. The few potentially habitable worlds that have been discovered are tens and hundreds of light years away, requiring revolutionary breakthroughs in interstellar travel technologies. However, perhaps humans won't need perfect copies of Earth to establish thriving civilizations among the stars. Modern breakthroughs in genetic engineering, artificial intelligence, and life support systems are paving the way for our species to adapt to the most diverse planetary conditions, which would be lethal for an ordinary human. In this context, Mars appears to be the most realistic starting point for humanity's transformation into a multi-planetary civilization. Despite the thin atmosphere and extremely low temperatures, the red planet holds reserves of water ice, carbon dioxide, and valuable minerals, capable, with advanced technologies, of sustaining human colonies. Of course, in their initial stages, the first Martian settlements will be entirely dependent on supplies from Earth. However, over time, they will be able to evolve into fully autonomous communities. Further expansion throughout the solar system will become possible thanks to the asteroid belt, which contains colossal volumes of rare metals and other valuable resources. The space industry will be able to extract these materials for the construction of giant rotating stations, recreating Earth-like conditions and eliminating the need to search for habitable planets. To reach the nearest star systems, interstellar vessels will be required, capable of transporting entire human populations on journeys lasting hundreds or even thousands of years. These autonomous ark worlds will need to sustain complex ecosystems and ensure social stability over tens of generations. This presents us with unprecedentedly complex engineering and social challenges that we will have to solve. Advanced artificial intelligence systems could play a key role in humanity's cosmic expansion, taking on the roles of explorers, terraforming specialists, and guardians of accumulated knowledge and cultural heritage. Artificial intelligence is capable of surviving in conditions lethal to biological life forms and operating across the timescales required for successful interstellar colonization. The development of consciousness transfer technologies could open the human mind's path to existence beyond a biological shell, making possible forms of space travel and planetary colonization that are inaccessible to people of flesh and blood. Digital consciousness will be able to travel between stars at the speed of light and inhabit artificial bodies designed specifically for particular alien conditions. However, venturing beyond Earth imposes new obligations upon humanity. For we might just be the only intelligent species in the galaxy. It's not inconceivable that we are the sole bearers of consciousness in the universe, capable of comprehending the laws of nature, creating art and culture, and experiencing awe before the cosmos's grandeur. If we truly are alone, or almost alone in this corner of the universe, then the preservation of intelligence in this part of creation hinges solely on humanity's survival and propagation. The decisions we make in the coming centuries could determine whether consciousness spreads among the stars or instead fades forever along with our home planet once it becomes uninhabitable. 26 incredible convergences that brought you into being gave rise to a species capable of comprehending its place in the cosmos and taking steps to preserve consciousness beyond humanity's cradle. Regardless of whether this is the fulfillment of some cosmic design or the greatest achievement of natural processes, we now bear the incredible privilege and responsibility to become guardians and disseminators of consciousness among the stars. Thus, your existence in this perfectly balanced universe is not merely a lucky coincidence for which to be grateful, but a true call to action. A call that compels us to do all we can to ensure that the spark of reason kindled on Earth does not fade, but continues to blaze across the galaxy for billions of years.